My name is Dr. Mike Murphy. I'm an assistant professor of computer science and information systems at Coastal Carolina University. In this lecture, I will begin discussing virtual memory. Due to the complexity of the virtual memory subsystem, the second part of this introduction will be given as a second lecture. We have previously seen that each process in a system can be given its own logical memory space. This arrangement allows logical pages to be mapped to physical frames without the need for physical frames to be contiguous, eliminating external fragmentation and increasing the degree of multiprogramming that a system can support. We can further increase the degree of multiprogramming in a system by recognizing that processes do not actually use all the memory in their logical address spaces at any given time. Parts of the program code, including error handlers and infrequently called functions, are not utilized often. Furthermore, arrays and other data structures are often oversized and used in sections instead of all at once. If we can swap unused pages out of memory and onto a backing store, such as a hard disk, we can fit more processes into memory at once, increasing our degree of multiprogramming. Furthermore, we can give each process its own large logical memory space, which can in fact be larger than the amount of physical RAM on the system. When we add a backing store, the general address translation process remains the same. Processes access memory using logical addresses, which are translated into physical addresses by the MMU. The page table is still utilized to store the page-to-frame mappings. However, we do add some complexity in that a frame could be swapped out to disk at the time when it is needed. The CPU must provide a mechanism to detect the situation and generate a fault that the operating system can handle to bring the required page back into physical memory. The process of moving pages or frames of memory back and forth between RAM and the backing store is known either as swapping or as paging. Historically, the term swapping referred to the movement of entire logical address spaces, or entire processes, between RAM and disk. Moving single pages, or frames, of data between RAM and the disk was called paging. In modern practice, both terms are used interchangeably, and the Linux kernel component that performs page movements is called the swapper. A single movement of a single page frame into or out of physical memory is called a page swap. Historically, Linux machines used a dedicated hard disk partition to store the pages that were swapped out to disk. Modern versions of Linux are just as efficient using a swap file, which is a regular file stored alongside other data in the file system. It should be noted that swapping is an optional feature, and it is possible, and even quite common, to run systems without any backing store or swapping capability. Most embedded Linux systems, such as Android devices, do not use a backing store. If memory cannot be allocated to a process on such a system, the process typically crashes. Now, page swaps are implemented by the operating system. Some assistance from hardware is required to determine when a page swap needs to be performed. When translating a page number to a frame number, the MMU checks to see if the corresponding frame is resident or loaded in RAM. If the frame is present, the memory access proceeds as normal. If the frame is not present in RAM, however, the MMU generates a page fault, which is a CPU exception that is similar in concept to an interrupt. A specific page fault handling routine is registered with the system, either as part of the interrupt vector table or using a separate structure for fault handlers. A page fault causes this routine, known as the swapper in Linux, to be invoked. It is then the responsibility of the swapper to locate the missing page on the backing store and load it into RAM, possibly moving some other page frame to the backing store in the process. The address translation process gains a few steps when paging is utilized. A process makes a memory request using a logical address in its private address space as usual. The MMU first checks the translation look-aside buffer to determine if the page-to-frame mapping is present. In the case of a TLB miss, the MMU must consult the page table to find the mapping. Once the mapping from page number to frame number is known, the MMU must next verify that the page is actually loaded in physical RAM. If the corresponding frame is available in RAM, the memory access proceeds as normal. However, if the corresponding frame is not in memory, the MMU generates a page fault, which is essentially a type of interrupt. If generated, the page fault causes the operating system to switch context to the page fault handling routine, which retrieves the corresponding memory contents from the backing store. Once this process is complete, the OS changes the CPU context back to the original process, and the memory access proceeds as normal. In order for the MMU to be able to detect situations in which a requested memory frame is not physically present in RAM, an extra bit must be added to the page table. This bit is set to 1 whenever the contents of a logical page are present in a memory frame. If the present bit is 0, the page has been swapped out to the backing store. For efficiency reasons, the TLB entry corresponding to a row in the page table must also store the present bit. You might have noticed that the terminology between page and frame is starting to become a bit blurry here. In general, we refer to pages of memory being swapped out to disk, even though the swap operation is actually moving physical memory frame contents. This fuzzy terminology is a result of historical evolution of the virtual memory subsystem. Now I'd like to take a moment to discuss the nature of backing stores as technology is changing in this area. Historically, the backing store was a mechanical hard disk drive, and a number of design decisions in the virtual memory subsystem still use this assumption. However, many systems now, especially embedded systems, have only solid-state storage. Since each block on a solid-state drive can be erased and written only a finite number of times, there is some question as to whether it is a good idea to use an SSD as a backing store for virtual memory. Many embedded devices do not use paging for this reason. Another issue with the backing store is that it is subject to attack via forensic disk analysis methods in the event the device is lost or stolen. Sensitive information, such as cached passwords and other credentials, might have been swapped out to the backing store, and these pieces of information could be recovered. One solution to this problem, which is available as an easy-to-enable option in Mac OS X, is to encrypt the contents of virtual memory. The downside to this approach is the addition of CPU overhead on top of the generally slow nature of the backing store hardware. Another approach to avoiding the issues of write limits and post-mortem forensic recovery of sensitive memory data is to use the Linux compressed caching, or comp cache, mechanism as a backing store. With this approach, a section of RAM is reserved ahead of time to create a compressed RAM disk, or ZRAM disk. When a page is swapped out to this ZRAM disk, it is compressed on the fly to fit into a smaller amount of memory. Whenever a page needs to be swapped in from the backing store, the page is read from the ZRAM disk and decompressed. Although the compression and decompression steps do result in CPU overhead, the comp cache system is still generally faster than using a disk or SSD as a backing store. Furthermore, comp cache is as secure as RAM against forensic analysis, particularly against recovering sensitive information from a system that has been powered off for a period of time.